Yeah, sorry, I would also record this meeting so that at least we can share the links after our talks. So again, to introduce myself, my name is Dr. Arnav Malik. I am working as an application specialist in Anton, Paar, Middle East Technical Center, Dubai. And in case if you have any queries regarding any of our material characterization instrument, you can actually share with me your queries at this particular mail ID. I would be really very happy to help you out. As far as the content of my presentation, I would be mainly discussing about the viscosity, its application and examples. Then we'll come to the fundamentals of viscosity measurements, where we will discuss about the mathematical formulations that can be used for a viscosity measurement in any rotational rheometer. Then we'll discuss about the viscosity behavior of various fluids. Also, we will discuss about the methods by which we can determine or measure the viscosity effectively, and we will discuss about how to measure a viscosity using a rheometer. And followed by that, after all our talk, we will be going through a practical demonstration of a rheometer with some sample measurements. To start with the viscosity, you all must be familiar with the flow behavior of various fluids. Now, flow behavior affects our day-to-day life. It means flow behavior usually comes into play with the simplest things such as food or some complex processing and structural application. Although the property of fluids have been known to the mankind from ancient times, however, this term to quantify a flow behavior of any particular fluid came into existence from the work of Newton's and Stokes. In 1920s, later, Professor E.C. Bingham actually combined flow behavior of not only fluids, but all of the materials and named it a rheological study. So basically, when we talk about flow behavior, it is, as you all know, it is how you, in simple terms, you can say that how your material actually flows under various circumstances, forces or stresses. When we talk about, before talking about the flow behavior of any material, first we should understand what are the different types of material that are available in this universe. And when I talk about the classification of materials, I am emphasizing on the material which you can physically see and observe. So basically, materials can be divided into 4 parts. On the left-hand side of your screen, you can see that materials can be either ideally viscous, like water and oils. These type of materials usually do not possess any structure in them. So even at a very slightest of force or slightest of strain, shear rate applied, these material tends to flow. Then material can be viscoelastic liquids like glues and shampoos. These type of materials do have some elastic structure present in them. And in case if you, if it means like in case if you are putting some excessive amount of stress or shear rate, these type of materials also tend to flow. When you talk about viscous liquids and viscoelastic liquids.
Sorry, Dr. Arnav. Sorry.
Yes. Okay. You cannot see the slides.
Yes, we just see the Anton Paar logo, and there are no changing in the slides.
Okay. 1 second. Let me check again. Let me reshare it. I'm sorry for this. 1 second. Wait for a second. Need to check. Now you can see? No, still no.
Still.
I'll share the video. Yeah, now I think. Just wait for a second. Yeah, now I think you can see again my screen.
Yes.
Can you confirm, please, Mr. Mohammed?
Yes.
Yes. Yes, we can see.
Okay, fine. Sure. Sorry for all the interruptions. Means like these days, means like in COVID era, definitely these type of WebEx actually keeps on changing the tabs and all those things. So sorry for all the interruptions and all those things. So let me start again. So again, I will just go to the content, what I am going to discuss today. So it would be basically the viscosity, its application and examples, the fundamentals of viscosity measurement. We will discuss about various behavior of fluids, and also we will discuss about the methods by which we can actually measure the viscosity. And then we will discuss about how we can measure the viscosity using a rheometer. And after all these topics, we would be having a demonstration, live demonstration, where I will measure one sample in a rotational mode. So let me come to the viscosity. So as I have mentioned, fluid behavior is known to means like mankind from a very ancient times. Although this term viscosity, that is, you can say a quantification of fluid behavior or fluid flow, came into existence in 16th century by the works of Newton and Stokes. And then later in 1920s, Professor E.C. Bingham actually combined this fluid behavior or the flow behavior of various types of material into the term Rheology. Now, before getting to know different type of flow behaviors in a material, we must know the classification of different materials which you can physically see. So materials mainly can be classified into 4 terms. On your left hand side, you can see materials can be ideally viscous. It can be, for example, it can be like water and oils. These type of materials usually do not possess any type of structure, and even at a very slightest of stress applied or shear rate applied, these material tends to flow. Then material can also be classified into viscoelastic liquids. Now, as the term indicates, viscoelastic, that means these type of materials do have some viscous property as well as the elastic property. The examples of these type of materials can be glues or shampoo type of shampoo, where you would find some elasticity present in these type of fluids. Now, when you talk about rheometry, viscoelastic liquids and viscoelastic and ideally viscous liquids can be measured using a rotational tests, and up to some extent viscoelastic solids. But mainly when we talk about viscoelastic solids with the example of say paste and gels, we can only measure these type of solids using an oscillatory tests. And finally, we can also have materials which can be ideally elastic like stone and steel. And these materials usually do not flow until some sort of ambient condition has been changed. So for example, when you talk about steels, steels also flow provided that you increase the temperature up to a certain extent. So ideally, you can say that all the materials that are present in this world are viscoelastic in nature, which means that they have some viscous effect present in them, and also they have some elastic present in them, elastic properties present in them. And in today's talk, we would only be discussing about the rotational test. That is, we would be discussing about the viscoelastic liquids and viscoelastic and ideally viscous liquids. Now, what is viscosity? I think all of you already know viscosity can be defined in simple terms as an internal friction or internal resistance towards the flow. So here you can see in the photograph itself, either your material can flow at a very easily, which says that the viscosity of these type of materials are very low, or it can flow with only in case if you are applying a increased force or you are applying a higher stress. So on your figure, you can see on the left hand side, you can see that this particular liquid is flowing very easily. That means this is a low viscous liquid. And on the right hand side, you can see that your material is not flowing very easily, meaning it has a high viscosity. Now, high viscosity is basically a result of an internal structure of a material. So when you talk about viscosity itself, viscosity is mainly dependent upon three factors. So first factor is the internal structure. As you can see in this photograph, on the left hand side, the liquid do not possess a strong internal structure. That's why it flows very easily. And on the right hand side, the material do have some internal structure, thus it has a higher viscosity. So viscosity is primarily dependent upon the internal structure of any type of material. Now, the second factor which is important in for viscosity characterization is an ambient condition. Now, in ambient condition, in case if you change the pressure or in case if you change the temperature, the viscosity will change. So even when you consider materials, most of the materials are thermorheologically very active. That means even in case if you increase the temperature by 1 degree Celsius, the material will change its viscosity. Same goes with the pressure. With even if you change the pressure by say 1 or 2 bar, there would be change in the viscosity. So ambient conditions while measuring the viscosity is very important. Third important factor for viscosity characterization is the external force. In case if your material do possess some residual stresses, or in case if you are applying some sort of external force on the material, the viscosity will change. So it is really very important when we are characterizing a viscosity or we are measuring a viscosity by any instrument to know whether any sort of external force is present on it or not. In case if it is, then definitely the viscosity value what we are seeking would not match. So these three are the main factors for characterizing any characterizing any particular fluid or viscoelastic liquids. Now, why viscosity measurement is important? Now, when we talk about the applications itself, there can be multiple applications where you need to measure the viscosity or you need to measure the complete flow curve. Some of those applications are, of course, in the petroleum sector, where viscosity measurement is very crucial for various operations. So when we talk about upstream operation, like fracturing or drilling fluid development, you need to know the viscosity of your fluid, so that in order to effectively use it for an application. When we talk about midstream, that is crude oil transportation or wet precipitation, in this case also you need to know the viscosity of your material in order to maintain the pumpability of your fluid. Then when you consider downstream operations, viscosity measurement is really very important, especially under temperature and pressure. Also, when you consider the byproducts of petroleum, that is asphalt and polymer, it is really very important to characterize, even for polymers, in order to get the molecular mass of any particular polymer, you need to know the viscosity or zero shear viscosity, which we will discuss in coming slides. And also for asphalt, there are various AASHTO and ASTM standards, which any asphalt manufacturers have to follow in order to, you can say, in order to develop asphalt or polymer modified bitumen. So petroleum is something which is very important and it requires a viscosity characterization. Now, another sector is lubricating oil. All of us are driving some sort of vehicle. Have you ever wondered what the grade mentioned on the bottle of lubricating oil means? So for example, in case if you see a lubricating or engine oil bottle, and it is mentioned, the grade, what is mentioned on that bottle is SAE 10W minus 40. That would actually give you the winter and summer grade of that lubricating. So the winter grade would actually tell you the temperature up till which that particular lubricating oil can be used. Because when you go with the winter grade at lower temperatures, the viscosity increases. That will affect the pumpability of that engine. So definitely you need to make your lubricating oil in such a way, and dependent upon the weather conditions of that particular country, in such a way that the pumpability of that particular engine oil is not affected at a lower as well as at a higher temperature, at a maximum temperature. So when you see SAE 10W minus 40, 10W would basically mean the winter grade, and 40 would mean the temperature operability of that particular engine oil in a summer grade. Other than petroleum sector, viscosity measurement is very crucial in civil and construction for applications like self-leveling and pumping behavior. Also, it is important for food industry for texture of the food, mouthfeel, and packaging. Definitely means like this is also something which is very important to means like important as far as application is concerned, because whatever you eat, how that particular material, food product will behave inside your mouth, viscosity can simulate that. So depending upon the viscosity and the consistency of your food product, you can actually see or actually determine about the mouthfeel of that particular product. So this is something which is very crucial, and most of the food industries use various viscosity measurement techniques in order to simulate the mouthfeel of that particular product. Another application is paints and coatings, where you can determine about the sagging, leveling, and behavior of a paint, and also you can determine the physical stability of your paint products. Cosmetics is one of the applications for viscosity measurement. Basically, the application is in designing the cosmetic product and defining its feel and flow behavior, because most of the cosmetic product that we use, they require certain degree of shear or shear rate, or say shear rate in order to apply. So for example, if you are applying any hair gel, so you take it on your hand and then you shear it very hard and then apply on your hair. So shearing is, or the viscosity behavior is very crucial when you are applying that particular hair gel on your hairs. Then another application for viscosity measurement in industry is adhesive. And again, in adhesive, it is very crucial. Viscosity measurement is very crucial in designing the flow behavior and depending upon desired application. And along with these applications, there are many more applications in pharmaceutical industries and say coating industries in order to measure the viscosity and to characterize the material. Now, what are the mathematical formulations that are being used in order to determine the viscosity? Now, when we consider viscosity measurements, we can consider, or we can just imagine a two-plate model where you can see over here on top left of your picture, a picture showing two-plate model where your bottom plate is fixed and your top plate is moving, and your sample is actually filled in between these two plates. So when we consider a viscosity measurement, or in case if your top plate is moving, the velocity and the height of the sample would give you the shear rate. So when we talk about the shear rate, it is basically the velocity at which this top plate is moving divided by the total height of the sample. The unit of shear rate is always in second inverse. And when we talk about the force applied on the sample because of movement of this top plate divided by the complete area, we will get the shear. So most of the times when we talk about a viscosity measurement using any particular rotational rheometer, we basically define the shear rate, that is given by the velocity divided by height, and measure the shear stress, which is given by the force divided by the area. And the basic boundary condition for a viscosity measurement is that we always have to consider a laminar flow. Once there is a transition from laminar flow to turbulent flow, the viscosity values would change. So it is really very important for any type of viscosity measurement to make sure that the flow what you have in your instrument is in laminar region, not in turbulent region. Also, in rotational rheometers, lot of you probably might are using different type of rotational rheometers. Shear rate, what we defined over here, that is velocity divided by the total sample height, is directly proportional to RPM. Because lot of rotational rheometers usually do not use shear rate as a term, they use RPM, especially when you talk about rotational viscometers. So RPM, what you input to the sample or what you input to in your instrument is basically directly proportional to the shear rate. And when you talk about shear stress, it's the outcome, or you can say which is the result, which is your main result, is directly proportional to torque generated. So whenever you see any rotational rotational viscometers, they mainly deal in RPM and torques. So those RPM and torques can be actually related to shear rate and shear stress. Now, when we talk about viscosity, viscosity is simply your shear rate divided by shear stress. So here you can see viscosity, which is represented by eta, is given by the shear stress divided by the shear rate. And the unit of viscosity is, the SI unit is millipascal second. Lot of quality control industries quality control are still using a unit called as centipoise. So when you look at this relationship between millipascal second and centipoise, so you can say that 1 millicentipoise is equivalent to 1 millipascal second. So both are somewhat equal. So, but most of the time, conventionally, still a lot of people designate it as a centipoise, but SI unit of viscosity is always millipascals. Now let us discuss about various fluid behavior. So usually fluid behavior can be classified or characterized into three main behaviors or three main ways. A fluid can be ideally viscous. So here you can see over here how the ideally viscous fluid behaves on this particular image on your right hand side, top right. Here you can see on x-axis we are varying a shear rate, as I have mentioned earlier. What shear rate is? Shear rate is basically the velocity what we have given to the upper plate divided by the total height of the sample. So x-axis is your shear rate and y-axis is your viscosity. You can see in case if we increase the shear rate, my viscosity value does not change. So this type of behavior is known as ideally viscous behavior, and also it is known as Newtonian behavior. So if you see anywhere it is mentioned Newtonian behavior, you can imagine that it's this that particular material do not change its viscosity with different shear rates. So irrespective of shear rate, you will have the same constant viscosity. Now, other type of fluids can be shear thinning and shear thickening. Now, shear thinning, when you talk about viscoelastic liquids, 90% of viscoelastic liquids are shear thinning in nature. And only few of liquids or viscoelastic fluids are shear thickening in nature. So what is the difference between shear thinning and shear thickening behavior? So here you can see on right hand side, middle and bottom image. In shear thinning liquids, the viscosity decreases with respect to shear rate. So just to give you an example of yogurt, if you stir a yogurt very fast, you would find that the viscosity or the ease of stirring increases and viscosity decreases. So these type of materials are also called pseudoplastic materials, or also you can say that these are shear thinning material. To give you an example, most of the emulsions that you are having, especially oil water emulsions, they are basically shear thinning in nature. Means their viscosity decreases with respect to different shear rates. Then we have a shear thickening type of fluids in which the viscosity increases with respect to different shear rates. So if you increase the shear rate, the viscosity will increase. You would find very few material with these type of properties of shear thinning where your viscosity actually increases with the shear rate, especially as far as application is concerned. Lot of research work I can share that lot of research work is going on for shear thinning liquids to be used as a bulletproof vest. So there are a lot of applications of shear thickening liquids where you would find that the viscosity of those type of viscoelastic liquids increasing with different shear rates. These type of materials are also called as dilatant materials. Also, in some cases, you may see in literature these type of materials to be referred as non-Newtonian materials, where your viscosity may increase or decrease with respect to different shear rates. To give you an example of a Newtonian flow behavior, you can see over here viscosity measurement results of a mineral oil. And here you can see on x-axis, we have a different increasing shear rate. And on the y-axis, you have a constant viscosity. So you can see the viscosity does not changes with respect to different shear rates. To give you an example of a non-Newtonian behavior, you can just watch this video and see the difference between a non-Newtonian and Newtonian fluids. So here you can see that this transparent fluid actually started falling very rapidly, but with time, when it reaches bottom, the flow of this liquid stops or minimizes, although this brown fluid is continuously flowing irrespective of sample height. So you can see now this translucent or transparent fluid actually the flow stopped, and for this brown fluid, the flow is continuous. This type of material is usually shear thinning material, and brown fluid is a Newtonian fluid. That means irrespective of sample height or effect of gravity, it continuously flows. Although in case of shear thinning liquid, at first it flows very rapidly under the effect of its weight and gravity, and as the level of these fluids lowers down, the flow actually stops. So these are like a shear thinning behavior, and this is your Newtonian behavior. Now, if you take an example of a shear thinning behavior for oil-water emulsion, you can see two examples where we have an undiluted oil-water emulsion and we have 10% additional oil-water emulsion. You can see the difference in the viscosity. First characteristics that you would notice is that these are shear thinning liquids. As you can see, with increase in the shear rate on x-axis, the viscosity of these emulsions fall. When you talk about even, that is undiluted oil-water emulsion, the viscosity is higher than E2, which is a diluted oil-water emulsion. Although the characteristics of both these samples are shear thinning in nature. And these are typical behavior of dispersions. So most of the emulsions that you have, they do follow this type of flow curve or this type of behavior with respect to different shear rates. Another example of a shear thinning liquid is a molten polymer. So in order to consider a polymer melt, you can consider it as a bowl full of spaghettis or noodles, where you can see all the molecular chains are entangled with each other. So whenever, in case if you are studying any polymer material or you are into melt rheology, you can always consider a polymer melt as a bowl full of noodles. So where each strand of noodle acts as a molecular chain. And when you see a bowl full of noodles, they are entangled with each other. So most of the strands of noodles are entangled with each other. Same way, polymer molecular chains are also entangled with each other. At low shear region or at a low shear rate, there is a constant entanglement and disentanglement in this molecular chains. Thus, the viscosity at low shear ranges are always constant. But if you increase the shear rate, you would find that disentanglement overcomes your re-entanglement. Thus, your viscosity decreases. And through these data, we can actually determine something called as zero shear viscosity. Now, this zero shear viscosity, which is eta zero, is very much helpful in determining the molecular mass of a polymer melt. So here you can see an example of the flow behavior of any polymer melt. Here you can divide it into three regions. The first region, you can say it is a constant viscosity region, which is given by eta zero, that is zero shear viscosity. And in this region, there is a continuous re-entanglement and disentanglement of your molecular chain. But as you increase the shear rate, the viscosity starts falling. That means in region 2, your disentanglement overcomes re-entanglement and your viscosity drops. And finally, in third region, you would find that now most of your molecules are completely relaxed, or you can say that there is no entanglement present in the molecular chain, and your each molecules what you have are independent of each other. So you will see again a constant region, and it is also represented by eta infinity, which is, you can say that it is infinite viscosity. When you talk about eta 0, which is given, which is actually a zero shear viscosity, this information of eta 0 would give you a molecular mass. Or in case if you are comparing two polymer samples, you can actually define what polymer or what type of polymers have a higher molecular mass and which one is having a lower molecular mass. The slope of the downfall of viscosity, that means region 2, will give you the molecular mass distribution. So for example, if you have a molecular mass, a narrow or wider molecular mass distribution, you can clearly see the difference in the slope. To show you an example of polymer solutions, you can see two polymer solution comparison, P1 and P2. Here you can see that P1, since the magnitude of the viscosity is higher with P1, the molecular mass of P1 is higher than that of P2. Although, when you look at the slope of the fall of viscosity or the region 2, you can say that the molecular mass of P2 is wider, and molecular mass distribution of P1 is narrower. So you can actually compare the molecular mass and also molecular mass distribution using a flow behavior of any polymer. Definitely means like there are other ways to determine the molecular mass distribution also, but this rheometry is also one of the techniques by which you can actually measure the molecular mass very much accurate. Another behavior what we have or in materials is a thixotropic behavior. Now, thixotropic material basically can be defined as the material which has a permanent structure. If you shear it, that structure would be completely distorted or it would be completely destroyed. And when you remove that shear, it will again regain its structure. So thixotropic behavior, you can say, is present in the material which has some sort of structure recovery mechanism. So most of the times these type of tests can be done in 3 intervals, where your first interval is always at a low shear rate, second interval is at a higher shear rate, and third interval again is at a low shear rate. And you can study how your structure of material is recovering. So it finds a very useful application in coatings. Here you can see a comparison between a gellant and a viscosifier. You can see that this particular experiment has been divided into 3 parts. The first part is at a low shear rate. The second part is at a very high shear rate. And the third part is at a very low shear rate. So when you start this experiment, you would have a high magnitude of viscosity. Then suddenly at a second interval, you would see a fall of viscosity. And at the third interval again, there would be some structure recovery. Now, if you compare the structure recovery of gellant and viscosifier, you can find out that the structure recovery of gellant is very fast. So you can see over here in red triangles, the graph at red triangles. So after a viscosity drop, there is a sudden structure recovery. Although for viscosifiers, this particular structure recovery is very slow. So if you are using these materials for coating, definitely means like gellant will have issues with sagging, and there would be a high wet layer thickness and very poor level. Although in case if you are using viscosifier only, you would have a good leveling, but the sagging would be too much in these type of samples. So ideally, in ideal case, you should always mix these two, gellant and viscosifier, in order to use it for a actual application of coating. So these type of characterization can also be performed using a rheometric measurements. Now let us discuss about various methods for viscosity measurement. Now, viscosity can be measured in a number of ways, and I suppose that a lot of you are already using some particular techniques in order to measure the viscosity. Conventionally, viscosity was used, or still is measured, using a flow cup, where you choose a flow cup according to various standards, fill your liquid on that flow cup, and let it flow to a cup. Now, the time that it takes for this liquid to empty or to fall on this particular cup can be indirectly converted into a viscosity. So there is a table, a standard table, which you can compare the time and determine the viscosity of that particular material. Now, when you talk about the viscosity, what you are getting using a flow cups, basically we are dealing with kinematic viscosity whenever we use flow cups, where you are actually measuring the time period of this liquid to flow and converting that time period to a viscosity. Another method is a glass capillary viscometers, which is still being used quite commonly. This method also gives you a value of a kinematic viscosity, where you would again note down the time of flow of that particular liquid and convert that time to a viscosity. Another method for viscosity measurement is falling ball viscometers, and Anton Paar do have a low vis 2000 M series of viscometers, which is using this technique. And these type of method is only suitable for very low viscous liquid. So in case if you have some material which are having a very low viscosity, less than 10,000 millipascal second, you can use this type of method effectively to determine the dynamic viscosity, and then you can convert that into kinematic viscosity. Another method of determining the viscosity is rotational viscometers again. Now, when we talk about rotational viscometers, it is quite similar to a rheometer, although rheometers can do way much more, or they can be used for a viscoelastic material too. And these rotational viscometers are mainly suitable for, you can say, ideally viscous liquids and up to some extent viscoelastic liquids. And the results that you are getting using these rotational viscometers are basically a relative viscosity. So you are not getting a dynamic viscosity using these rotational viscometers. It is a relative viscosity which you measure from these rotational viscometers. Now, the major limitation of all these methods is that all these methods are a single point measurement system. That means you fix the RPM and you measure the viscosity at that point. Now, in order to get a complete information of any particular fluid, it is very important to get a behavior of or flow behavior of your material at various shear points or RPM. And these methods or these instruments can only be used for a single point viscosity measurement. which gives you an information about viscosity, which is also quite suitable for Newtonian fluid, because the viscosity value does not changes with respect to shear rate. But when you are dealing with non-Newtonian fluids, shear thinning or shear thickening one, these methods would not give you a complete information. Now, in order to get a complete information of your system or your material, you need to use a rheometer, which can actually characterize your materials in a multiple way. Now, just to give you an example of comparison between a flow cup measurement and a rheometer measurement. In rheometer measurement, you can see we are getting a complete flow curve from very low shear rate to very high shear rate. Although in flow cups, you can see we are getting information about viscosity of this material to a very limited range. So if you compare these three binders or these three printing inks, you can see that if you are using a flow cup, you would see that the viscosity is somewhat similar. Although when you go to higher shear rates, which flow cup is not able to give you, you can see that there is a substantial difference in the viscosity. And printing inks, definitely, most of the application of printing inks are at higher shear rates, because so you need to prevent excessive amount of spattering. So in this case, definitely, you can see that in case of S1, sample S1, there would be very less spattering. Although in case if you are using S3, there would be a lot of spattering when you are printing it on a paper or a piece of film. But flow curve would give you very limited information about the characteristics of these printing inks. Also, using a rheometers, you can perform a high pressure studies, and high pressure studies, of course, do have its applications in petroleum sector, that is oil recovery, in drilling fluids, fracturing fluids, in petrochemical industries for polymer melts, and also in a food industry for starch dispersion and plant oils. And when you look at the pressure vessel or pressure cell in rheometers, it looks like this image, where you can put your sample inside this particular vessel or this sample cell and externally apply pressure from this steel tubings. This is an example of a high pressure measurement on crude oil at 50 degrees Celsius. You can see at ambient pressures, the sample or the crude oil sample acts almost like a Newtonian fluid. And if you increase the pressure, there is a transformation from Newtonian to non-Newtonian. So at a higher pressure, you can see at 1000 bars, you can see that the magnitude of viscosity is higher and it falls with respect to different shear rates. And here you can see that we can also operate at a very, very high shear rates. So here we have used this particular measurement up to 5000 second inverse. Another example of a high pressure study is on the drilling fluid. Now, ideally, when you talk about drilling fluid should not change its behavior under pressure. So, for example, if you are measuring a sample, a drilling fluid using a rheometer in an ambient condition, the viscosity should be same as what you would be measuring it in a high pressure conditions, because it is very important that drilling fluid, because most of the applications of drilling fluids are under high pressure, and it is very important to maintain the flowability of that particular drilling. So you can see over here an example of drilling fluids. Here you can see on x-axis there is a shear rate, and on y-axis you have a viscosity. And we have measured the drilling fluid at ambient conditions and also at 1000 bar of pressure at 30 degrees Celsius. So you can see over here that initially the magnitude of drilling viscosity is high, and it decreases with respect to increasing shear rates. And so you can also see that even at a higher pressure, there is no change in the viscosity. So ideally, when you look at the crude oil example, the viscosity increased with uh, with the with high pressure. Although in case of drilling fluid, even at a higher pressure, the viscosity curve or flow behavior is completely replicating the ambient condition, which is actually desirable. And also when we consider drilling fluid, it mostly has to be measured at higher shear rates. So you can see even at a higher shear rates, it is maintaining the viscosity of that particular of ambient condition. Another important type of studies that we can perform using a rheometer is a temperature dependent studies. Definitely temperature dependent studies are very useful in determining the softening, melting, or solidification and crystallization of any particular material. Even you can get an idea about the cloud point and the core point of your material, of your sample, using a temperature dependent study. Here you can see an example of a temperature dependent study on a mineral oil. Here we have an x-axis we have actually converted this plot as per Arrhenius equation, and you can see this particular region is a high temperature region, and this is your low temperature region. So you can see over here, if we go through high temperature to lower temperature, and your y-axis is your viscosity. The viscosity increases from going to high to low temperature. At a certain point of temperature, you would find a sudden inflation. That inflation would mean that the crystallization had started to occur, and will also give you an idea or about the pore point of that particular material. So you can exactly point out the cloud point using these type of temperature studies, and also you can get an idea about the pore point of your material. The crystallization is definitely will happen up to certain extents, and after that, if you lower down the temperature further, there would be somewhat a saturation of the magnitude of the viscosity. So you can say that at that particular point, your material acts more like a viscoelastic solid type. Now there are various type of geometries that are being used to measure in a rheometer. So basically we are using three type of geometries, that is concentric cylinders, cone and plate, and parallel plate. When you talk about the accuracy of these geometries, you can say that concentric cylinder is the most accurate one, but it can only be used for low viscous liquids and also for viscoelastic liquids. Definitely you require a higher sample quantity in concentric cylinders compared to other geometries, and also it is little bit difficult to clean. Then we have a cone and plate type of systems. Now cone and plate type of systems are also very much accurate. It can be used for various liquids, dispersions, but only limitation of this cone plate type of geometry is the particle size of your dispersion. So for example, if you are having a particle size more than 10% of the gap, then you should not use it. So for example, if you are using a cone plate 25 with the gap of 50 micrometer, and your maximum particle size is say more than 5 micrometers, then you should not use the cone plate, because those particles may form some sort of a structure at the middle of this cone plate, which is conically shaped. So definitely the results what you would be getting would alter. So cone plates are always limited to a limited particle size. Then we have a very common geometry which is widely used for various applications, that is parallel plate. Now parallel plate do not have these type of limitations, and you can use parallel plate for various dispersions with various particle sizes, and it is very suitable geometry for gels, paste, soft solids, and polymer melts. Only the limitation of this parallel plate compared to cone plate and concentric cylinder is that it is less accurate. It is less accurate because you can see, because of this flat surface of this geometry, the stresses induced would be different at the center than on the edge. And what you are measuring is an average of center to edge stress. Definitely, when you are rotating or when you are shearing any particular sample using a parallel plate, the stresses generated on the edges would always be higher than compared to in the center. So that's why the accuracy of this type of geometry is a little bit compromised. Although still, this is widely used and widely accepted geometry for various type of materials. Now, when we talk about Anton Paar viscometry and rheometry solutions, we have from low to very high-end rheometers. You can see we have a rotational viscometers, our Visco QC series. Then we have a quality control rotational rheometers, our Rheolab QC and MCR X2 series. And also we have high research grade rheometers, which are our MCR XX2E series. Now, next question is how to measure the viscosity. Definitely, rheometers can be used in two ways. It can either be used in a rotational mode or it can be used in an oscillatory mode. Today, we would be demonstrating rotational mode, and I'll show you how we can actually measure any particular sample using a rotational mode in a rheometer. And also, as far as the pressure range and the temperature range using a rheometer, so the maximum pressure range what we can achieve using a rheometer is 1000 bars, and the temperature what we can achieve is around 1000 degrees Celsius. So most of the applications can be we can actually use are having applications under 1000 bar and 1000 degrees Celsius. So most of this particular temperature and pressure range covers most of the application. So from there, thank you very much for listening. And I would now ask in case if you have any questions, and then we can switch to our other presenter to share his work on this rheometry. So in case if you have any questions, there was some disturbances in the starting, so I'm sorry, still sorry for that. But in case if you have any questions, you can ask.
Thank you, Dr. Ornov, for your very nice presentation. And now we will stay like 5 or 10 minutes waiting for your questions in the chat box, or you can raise your hand and talk. And then we will continue with Dr. Muhammad Al-Busayfi. So please, if you have any question, please don't hesitate to type in the chat box.
Anyways, we can continue with the Dr. Muhammad, and we will then, in case if meanwhile if you have any questions, we can of course discuss it later. But I would say that we can continue with the next session.
All right. Dr. Muhammad Al-Busayfi, I think there are no questions in the chat box, so you can begin your talk. And if somebody have any question, he just should type in the box.
Hello, do you hear me?
Yes.
Yes, we hear you, and we see the screen very well.
Thank you, Mr. Arnaud, for your very nice presentation, which give a very good idea about basics of rheology and instrumentation you make in your company. I would like also to welcome all our online guests all over the world. And I wish to share with you very pleasant time and useful time. As scheduled, this second part of today's first day of our 2 days certified course, as you mentioned, it's about rheology. And I would like to share with you some ideas from our rheology lab here in LBI. First, I would like to give a brief.
Dr. Muhammad, you are muted. Can you please unmute?
Oh, okay. It's okay now?
Now it's okay.
Okay. So I first will give you some, share with you some views of the LBI. Sorry. Do you see the screen?
We see the first slide, basics of rheology.
Yes. I'm just trying to fix this.
You might close the share screen and open again. Maybe it works.
Okay. I'm just trying to.
Yeah, sorry. Yeah, I was on mute. But you can share now. 1 second.
So.
Yeah. 1 second. And now I think you can share. Please try. Cancel it and you can share.
Okay. Screen. Okay. I'm trying to share the file.
Yes, 1 second. You don't need to. You can click on viewing rheology presentation on your screen and probably cancel that and then share it again. Yeah.
Okay.
Now I think yes.
Okay. So I welcome you again. Sorry about this interruption. Rheology lab at LBI. First, I would like to, as said first, to welcome all and to mention that, as you mentioned, the rheology is a common concept we share with you. Rheology is serving different industries, so rheology has a place everywhere. LBI or Petroleum, Libyan Petroleum Institute, formerly called PRC, was established in 1977. We have over 40 laboratories specializing in different branches of industry, upstream and down. We cover upstream and downstream activities. Also, mainly we provide high quality laboratory testing services and technical studies in fields of exploration, reservoir exploitation, oil and gas processing, geological and geophysical data management, and all about environmental monitoring aspects. Rheology lab is among other labs. We provide technical support to the Libyan oil sector. Myself and Dr. Fathia, she's the Rheology lab supervisor, are happy to tour you through our Rheology lab to see different equipments, activities, and to review some of work being carried at this lab. This view is showing some of the equipments we have at the Rheology lab. We can see here the differential scan calorimeter, which we use to characterize different materials, such as waxy crude oils. Another views here with our rheometer, which we use for studying the rheology of crude oil and other materials. Here we can see the Torby scan, which we use, which we'll talk about later in studying the compatibility of crude blending. This is all views from the inside the lab. So it gives you an idea about what we have inside in our laboratory. Here we have a nice view of the CBM, which is the cross-boiler microscope, which we use to study the morphology of wax in the crude at different temperature, and we can study the crystal size and crystal distribution at certain conditions. So this is a very important equipment we use in our lab. The main objectives of our rheology lab is to provide services and to help companies in mitigating production and transportation problems, which, as we will talk about in this next few slides, we'll talk about the characterization of waxy crude oils and trying to mitigate problems of wax precipitation. So we use different techniques, as Mr. Arnaud stated in his last presentation. We use dynamic properties. We study characterize the dynamic properties of crude oil with different techniques, isolation and controlled stress techniques. So we can extensively study and determine the waxy crude oil properties at different conditions. Since the waxy crude can represent all conditions Mr. Arnaud talked about, from when it's quite hot, it's Newtonian fluid light, or it behaves like a Newtonian fluids. As the temperature dropped or decreased, so the wax start to show up, and it goes through other regions such as the viscoelasticity, and then end up to the at freezing or at Bohr point or less than Bohr point. The crude start to behave as elastic like. Also, we use the rheology to select different chemicals as additives to mitigate the wax problem. So rheology we use it at our laboratory as a method to study or to select among different chemicals to check which chemical will perform better than others. So usually, sometimes we receive different chemicals to be tested for which one will perform best for such crude. Also, in our laboratory, we as we mentioned earlier, we perform compatibility studies for crude oil blending. Sometimes when more than crude has to share a pipeline to be shipped to the terminal together, so we have to make sure that the crudes are compatible and no asphaltene precipitation will occur from such blending, which is quite very important for the producing companies. Also, one of the work we do and activities that we provide we provide or multi-phase simulation studies with their necessary data. So we carry on our work with using the rheometer to find out the whole spectrum of viscosities pointing to a certain shear rate. This data is very important for simulation studies. Also, we carry research in waxy crude crystallization, effect and mechanism of chemicals or wax chemical as a wax inhibitors in mitigating the paraffin wax. So this is some of the main activities we have in our laboratory. Libya, among other countries, produces waxy crude oils. As most of you know that more than 30% of world production is in sort of waxy crude oil. So waxy crude oil is all over the world, not only in Libya or Egypt or all over the world. They have this type of crude. We don't consider wax as impurities as some may think of. Wax is a hydrocarbon with different or with a certain range of carbon length. Waxy crude oils, they have many advantages, such as usually they have quite high API, as you can see on the screen, that the API minimum we have 25 and goes up to 43, which means that these crudes have a very good yield or quite high yield of low boiling point products, which is valuable as fuels. Also, usually most of waxy crude oils considered as environmentally safe, since it has a quite low level of sulfur. So the only thing is the wax content. Libyan crude oils have a wax content ranging about from 8 up to 29% of wax. That's make the pour point from ranging from 0 up to 51 degree, which needs a special care, especially when at winter condition. So at winter conditions or winter season and operation of subsea pipelines, dropping the drops of temperature, especially at night, below the wax appearance temperature of the crude, so the waxes start to appear and change their phase from liquid droplets in the bulk of the crude to solid crystals, which start to totally or partially reduces the pipe diameter and reduce the production rate. Usually, the journey of waxy crude oil in the reservoir, usually the temperature is higher than the gel point or the wax appearance temperature. And at this condition, there is no problem with wax. The waxy crude oil, like any other crude, have no problem. But once it gets up to the surface, and for any case of emergency shutdown or any pumping problems, failure, and the mechanical problems or malfunction of the pumps, and any stoppage and of the flow with temperature decrease, we start face the precipitation of wax and the surface facilities and the pipeline. So it's a matter of temperature. Here we can, this sketch diagram shows a pipeline where the crude is stagnant inside it, and the temperature is lower than gel point. The oil is stationary for some time, say 1-2 hours or 1 to 3 days, so it becomes solid. So in this case, we need to mitigate this problem to find out what pressure is needed to restart this pipe after certain shutdown period. As any waxy crude oils or paraffin consisted of long chain saturated hydrocarbons with a carbon chain length from, say, about C18 up to C75 or more or higher, and that's will keep the melting point in the range, say, ranging from 40 to 70 centigrade. As we mentioned before, from the reservoir, when the crude is produced, it's hot, and through the well tubing, it will start precipitate. When it's hot, it's like any Newtonian fluid. Just one viscosity measurement will be enough to calculate any design parameters. However, once the temperature is dropped or reduced and reach the wax base temperature, we start see the precipitation of macrocrystals and the crude flow behavior, as the rheology tells, departure from the Newtonian state or Newtonian condition to a non-Newtonian behavior. Even the non-Newtonian behavior gradually changes up to, as we said, at the Newtonian behavior, we have a liquid-like crude. One viscosity is enough to describe it, since the viscosity does not change with the pumping rate or flow rate. The viscosity will be a function only of temperature, as you know. However, once it started moving from the Newtonian region, going toward non-Newtonian behavior, we need more than one viscosity. So at each shear rate, we need a viscosity for that shear rate. So one viscosity measurement will not be enough. We need it for the whole range in order to get the necessary data for design or production process. As we mentioned before, what happens inside the pipe temperature is the main effect. Also, the composition of the crude, the percentage of wax inside the crude oil. Once the pipeline is hot, there is no problem. Crude is hot, there's no problem. But for any sudden shutdown or for any other reasons, for heating failure, prolonged any extended period of shutdown, so a wax core oil blood structure forms as a result of differential cooling and diffusion. Hence, care have to be taken to correctly estimate the extra pressure to be exerted in order to move and break the wax to flow through the pipeline. As a result of the temperature gradient across the pipe, corresponding gradient in the size of wax crystals will form. Smaller crystals at the wall increasing in the size towards the pipe center. So we will have small wax crystals stick to the pipe wall, but the other layer of wax which will come on this first layer will be increasing in the size. So it will have higher crystal size. Wax crystal metal interfacial area will be large. Therefore, strong adhesive forces at the wall. So these forces will grab the small crystals to the wall. It will be difficult to remove. However, the wax crystal oil plug interfacial area, so the area between the wax crystals and the plug, oil plug, will be small, which result in weak cohesive forces. Clearly, rheological characterization must take note of effects of temperature, cooling rate. Therefore, all these will be relevant in the restart of any gel pipeline. More clarification of this, of the phases of wax precipitation. First, at the beginning, at the first stage, the wax crystals formation, individual wax crystals tend to disperse in the bulk of the fluid instead of depositing on the surface. So that's at the beginning. Second, when the number of wax crystals becomes larger enough, or if other nucleating material such as asphaltene or formation fines or clay, which is usually comes with the crude, or corrosion products are present, the crystals may agglomerate into larger particles. So, as we all know, that crude oil is not a pure material. It's a mix of a limited number of components, as we mentioned. These larger particles then may separate out of the fluid and form solid deposits. So this is the problem now. The question is, what the minimum restart pressure of these pipelines? So first, as we see in the first drum here, which is represents the pipeline, when the oil is hot, so the wax is dissolved. As the pipeline or the pipe wall start to cool, the wax crystals start to form and accumulate on each each layer will accumulate on the previous layer till we finally reach the final wax core oil plug structure. So the pipe will be pipe diameter will be totally blocked with the wax. And in this slide, we see it clearly here. The inside diameter of the pipe decreases till the pipeline blocked totally, or the cross section of the area of the pipeline is blocked by the wax. To show the gelation and deposition of these paraffin gels in crude pipelines causes major transportation problems by reducing the flow efficiency. Regarding the wax deposition mitigation, there are many approaches companies used. However, it can be divided to two main approaches. The first is to prevent or reduce the occurrence of the deposition. How we can do that? By keeping the flow temperature well above the watt or wax appearance temperature. That's by in some pipelines they use a reboosting station when they reheat the crude, as we have in our fields here in Libya. They use at certain distance, they put reheating furnaces feeded by the gas in order to keep the flow temperature, the crude temperature above certain limit. Another way is to also to try to keep the flow rate up certain limit in order to ensure mixing during the flow and prevent any deposition to take place. The second, once this failed, and of course after sometimes that depends upon the conditions we just mentioned. If the deposition occurred, so it has to be mechanically removed. They used bigging, and the bigging time or period, of course, bigging costs and may even affect the integrity of the pipeline. However, at certain time they have to clean the pipe with the bigging tools, which Dr. Fatia will show in her presentation. The second are to mechanically remove and treat the deposition after it's already occurred. However, in order to select the most economical and technically suitable method, the waxy crude properties have to be accurately characterized. So we come here to need for the rheology to give us a clear and full picture about the properties of our crude in order to mitigate the wax by, say, using some chemicals, or even to do the mechanical bigging, we have to know the strength of the wax inside the pipe. So rheology is the key element here in solving or providing such information. The diagram we have here on the screen right now, it shows us the different states of the crude once it's flowing in the pipeline. As the temperature decreases, we start see different curve slopes. So once it's hot at the beginning, say at 80 degrees centigrade, so the viscosity will be low. Also, it will be stable. There's no change. The rate of change in the viscosity will be very low. Once the crystals start to form because of the temperature drop, we start see the change in the slope of the viscosity versus temperature curve. However, this slope continue to increase. So first we have the wax appearance temperature, which can be considered as the first crystal or crystals to appear, which we use the differential scan calorimeter to measure this property. And next, what will come the gel point. So gel point, when the crystals form in bigger quantity, bigger number, and the gel point temperature when the first or when for the precipitated wax formed a structure or a network of wax. So at the wax appearance temperature, we have just 1 or 2 or 3 crystals. At the gelling point, so the structure become mature and would be very obvious that we have network of wax crystals. A number of wax crystals forms the network. So as the temperature continue to decrease, this network becomes stronger and stronger, and we reach the Paar point. Even at Paar point, it's suppose we call it Paar point because at this temperature, the crude still can be poured. However, at few degrees below this Paar point, we see a sudden increase in the slope of the curve, of the viscosity curve, and we see high viscosity or maximum viscosity. So in this case, our crude behavior is reaching the viscoelastic or the elastic limit of the visco behavior. So at the beginning, we have Newtonian behavior, then viscoelastic properties start to take place, ending up to the elastic form. So we can conclude here that waxy crude oil can present all different types of behavior. What makes that happen is the temperature and the wax content of the crude. However, we reach the precise characterization of the waxy crude. In order to carry on this job, as we mentioned, rheology is the key for characterizing the waxy crude oil. However, we have different techniques which helps or complement the work of the rheometer or the rheology. We have the different equipment, just as the gas chromatography. Also, determination of the watt or wax appearance temperature using the differential scan calorimeter. In addition to that, observation and studying the gels forms using the cross-polar microscopy, CBM. So the rheology below, at and above watt using advanced type rheometers. The gas chromatography technique, as we can see here in this slide, we have the rheometer, which is the CVO, and you have the CBM, also the differential scale calorimeter, and the gas chromatography, high temperature gas chromatography. As we mentioned earlier, that the crude oil is hydrocarbons with different molecular weight and carbon chain with different lengths of hydrocarbons. So we use the GC here to give us an idea about our crude different carbon numbers. If you look here at the graph here, we can see which is the comparison between the ABU crude oil and ABU treated with 20% Certica light crude. We see the blue columns here are different than the others, which give us an idea what happened when we diluted the crude. So the carbon, the high carbon chains, which is from carbon number, say 29 up to 36 or 35, has been broken and moved to the low carbon number molecules, which does not cause a problem or cannot make trouble once the temperature dropped for the crude oil temperature drop. So the lower carbon number molecules make the crude the ability to move with less viscosity. Also, we have the differential scale calorimeter, which is DSC. The purpose of the DSC is to measure the heat flow of the waxy crude, subject to set of cooling rates, and determine the heat curve. So the appearance from the heat curve, the appearance temperature, wax appearance temperature, and the wax precipitation at any temperature can be determined. We come over to the cross polar microscopy. This type of instrument provides valuable information regarding it gives us the image and structure of the morphology of the wax and the crude, which form upon cooling, size of crystals and size distribution of formed crystals as a function of temperature and cooling rate can be seen and quantified, which is very important data for which complements any rheological study. Here we can see different the effect of cooling rate on average crystal size and density for ABU crude oil at 30 degrees centigrade. So the pour point of this type of crude is about 39, and when we reduce the temperature below the pour point, we could measure the C and detect and measure the crystal size and see the difference between the crystal size of this crude when it's cooled, say from 80 degrees centigrade down to 30 degree at different cooling rate. From this photos, we can see clearly that extending the cooling time for the crude give us higher crystal size and less density number. Here in the rheology or rheometer, we can see the measurement of viscosity at different temperature for this is a dynamic cooling, which is represents the normal pipeline operation at 10 reciprocal second. We can see the beneficial testing the performance of FOX inhibitors, addition, reducing the parent viscosity, hence the pumping pressure. So here we can see that rheology can be used as a selection tool. And this flow curve, the black one here is the black curve is the temperature viscosity of APU crude without any chemicals, just pure crude, no chemicals added. So we can see here at temperature less than 65, we can see the temperature from 85 up to 65 as constant viscosity, which represents the Newtonian behavior of the crude when it's hot. Once it started to cool down and approach the wax burst temperature, we can see a sudden increase in the viscosity and continuing to increase with a certain slope or certain rate, and the rate after 45 degrees centigrade, the rate of increase of viscosity exponentially increased. On the other side, we can note here or see the blue and red curves, which represents the viscosity of the same crude, but treated with other chemicals, with a certain dose as a ppms, and we can see the clear change in viscosity and viscosity increase. So here we can use this. We can say that this protocol is very useful in distinguishing which chemical will perform better for this crude. As you know, every crude has its own properties. What's said about a crude cannot be said about the other crude. So the crude to be treated has to be looked over, especially for it. If we find certain chemical is good for this crude, it might not be good for other crude. So we find this method is better and it's more advanced and gives very clear idea about the performance of the chemicals at different shear rates, at different flow rates, or at different cooling rates and different temperature. So many companies use the Paar point method to test the performance of their chemicals, and from now, I think many or most of the companies will depend on this type of technique, and that's just discard the Paar point measurement technique, which is quite old and inefficient. Oscillatory techniques also is designed to measure not only the yield point, we mean here by the yield point as you mentioned before, but also the viscoelasticity of waxy crude oil gels through the application of sinusoidal shear deformation and the measurement of the corresponding stress response. So this technique is quite important in studying the viscoelastic behavior. So, in this technique, as mentioned before, the measurements are conducted initially in the linear viscoelastic range at very small stress and frequencies that do not break the gel structure. So we are taking care that we just trying to study the gel property. Breaking the gel will not be the right way. So we study the G prime and G double prime. We measure it at a region when the gel is structure is unbroken. So the G prime and G double prime, which presents the elastic and viscous module, are independent of strain amplitude. So yielding is then detected when the viscoelastic region ceases to be linear, as shown in the figure below. So this is an idea to measure the one way to measure the yielding in a solitary flow condition. However, the control stress rheometry also do the work as we see here. So the controlled stress technique, so this means the application of a constant shear stress. So we select a constant shear stress to a gelled, of course, of a gelled waxy crude oil in a cone and plate or plate and plate geometry provides the experimental condition which is similar to the pipeline itself. So just mimicking the pipeline condition, and that most pipeline systems which operate using centrifugal pumps apply a controlled pressure drop rather than a fixed rate of flow. From the experimental point of view, it's much easier to measure very small displacement at fixed torque than it is to control the equivalent small rate of rotation and measure the resultant torque. Here, and this graph here, we see the effect of temperature on ABU crude oil and treated one. So 5-degree differences makes a big difference in the flow behavior of the, although it's non-Newtonian, but we can see an increase in the yield stress also in the thixotropy of the crude. The second graph here shows the using the controlled stress rheometry to measure the different yield stresses, such as the elastic yield stress and the static yield stress and the flow yield stress as modern rheology classify. Anyway, I hope that I didn't talk a long time. Throughout this presentation, I hope that we succeeded in presenting our rheology lab objectives, movements, and parts of its activities and capabilities in supporting the oil industry in Libya. What is presented in this lecture is about the rheology of waxy crude oil, but it's not the end of the story. We have also still other rheology of drilling fluids, rheology of asphalt binder, rheology of polymers, rheology of lubricants, and so on, greases, and so on. So at the end of this first day of this training course, we conclude that rheology is vital for the world oil industry. Anton Paar successful innovations of rheology equipment complements the efforts of Libyan Petroleum Institute as a service provider use such technology. So I thank you all for your patience, and I hope I didn't take much time of your time. So I will be happy to receive any comments or any question, and we hope that our collaboration with the Anton Paar it will be strengthened in the future, and we will have more events to share. Thank you very much.
Thank you, Dr. Al-Busimi, for this very insightful presentation. Means like it was really very good, and the introduction what you have given for waxy crude oils, different properties, various ways of characterization, it was commendable. And now we would switch quickly to the demonstration part, where I will just measure a few samples, and you can actually see how the rheometer actually works. So just I suppose you are already seeing your screen video of rheometer on your screen.
Yes.
Just go over there. Yeah. So yeah, so this is how a rheometer looks like. I think most of you, and especially Libyan Petroleum Institute, has been doing rheological studies for quite a period of time, and they have this type of expertise in your country to have rheological training sessions for different users. But those who are not familiar with the rheometer device, so this is a rheometer. This is how it looks like, and where you can see over here on the top, we have a motor head, and motor head. This particular part you can say is a heart of any rheometer, because this rotor or motor what we have, it gives the RPM or shear rate to a sample and measures the torque, or vice versa. So basically, rheometers can be worked in two modes, as Dr. Al-Busimi has said. So it can work as a controlled shear stress mode, or it can work as a controlled shear rate mode. In controlled shear rate mode, we are giving some RPM to the sample. That is, we are controlling the shear rate and measuring the shear stress. On the other way, if we are working in controlled shear stress mode, we are controlling the shear stress and measuring the shear rate. Either way, you can get a flow curve of any particular material. So when you look at this rheometer, you can say that this is an heart of a rheometer, where you have a motor head. It deforms the material as well as it measures the torque or stress. Then we have an air bearing coupling. You can see over here, most of the rheometers nowadays use air bearings. Now, basic advantage of using an air bearing is that it reduces the internal friction and increases the torque measurement capability of any rheometer. So here you can see this rotates, and when you rotate it manually, you would find very less internal resistance. So this will actually enable any rheometer to enhance its torque measurement capability. And this is the coupling where we need to fix our geometry. So in this case, we have different sort of geometries which we will use to measure a sample. Then we have a hood. This is a top cover for sample measurement. And this is active hood. That is, it is Peltier temperature device. So this particular hood can go from minus 40 degrees Celsius to 200 degrees Celsius. Yes.
Sorry, no. Dr. Mohammed Al-Busimi, could you please turn off the share screen so to be able to see the camera in full screen?
Sure. Yeah, sure.
Yeah.
Hello, Dr. Muhammad.
Yes, I'm trying to.
All right.
Can you? It's all right now.
No, not yet.
Okay.
Yeah, you can actually.
هذا الشيء.
Yeah, 1 second. Let me do it 1 second.
Okay. It's okay now.
Yeah, I
It's
think
okay
now
now.
it is fine. Yeah. So those who have missed, this is the motor head or the heart of a rheometer, which gives an RPM and also measures the stress. Or this is the air bearing coupling what we have in order to reduce the internal resistance and to enhance the torque measurement capability. We have an active Peltier hood. This particular active Peltier hood can actually go from minus 40 degrees Celsius to 200 degrees Celsius. And so ideally, as Dr. had previously said, most of the samples are very much temperature dependent. So even a change of 1 degree Celsius, the viscosity value or complete flow curve may change. So it is really very important to make sure that there is a minimal thermal gradient on your sample, or there should be a very good thermal homogeneity throughout. So that's why it is very important to use this type of active hood, so which enables a user to heat its sample from the bottom and from the top. So this is something which is a very unique feature of Anton Paar rheometers, where we have this active Peltier hoods. And then again, when you look at the bottom plate, this is the bottom plate where we actually keep our sample. Now, this is also a temperature control temperature device, a Peltier temperature device, which can go from minus 40 degrees Celsius to 200 degrees Celsius. So in case if you would like to do any time dependent study or temperature dependent study, or any set of different means maybe oscillatory studies, rotational rheology, for all that you can actually use this type of Peltier temperature plates and the hood. Also, I would like to show you a glimpse of pressure cell that we have. So this pressure cell, what you can see on your screen right now is 150 bar pressure cell. And this pressure cell, in order to use this pressure cell, we need to remove this Peltier plate and put another Peltier cup, means concentric cylinder type Peltier temperature device, and put this pressure cell into that. The pressure can be applied using a gas. So this is 150 bar pressure cell. So it can go up to 150 bars. And usually the temperature device that you are using with this pressure cell is can go from minus 20 to 200 degrees Celsius, or up to, in case if you are using an electrical temperature device, then even you can go up to 300 degrees Celsius. We have different sort of pressure cells. Of course, this is one of the pressure cell which is something with lot of people are using currently. So to device, you only have a motor head, temperature device, and rest of the things are controlled by the software itself. So I'll put some sample. This is some surfactant sample that I have. I'll just put it onto the bottom plate. and then we will look at the software interface. So I'll just share my screen. Just wait a while, just share my screen. So now I suppose you can see the screen. So this is how the software interface looks like, where you can see different sort of tests that are already present in this software. So you can see we have a flow curve, viscosity curves, and we have different project templates for different applications as per standard. We have a separate thixotropy tests, creep and recovery, stress relaxation. So all the tests which are very frequently used are already present in this interface. You can also see we can actually move the motor head up and down very easily through this navigation panel. So here you can see I have a navigation panel where I can move, I can do the zero gap settings, I can reset the force in order to remove any external force from the geometry, and I can also means like set the temperature from it. So for example, right now, if we want to measure at 25 degrees Celsius, so I'll just select over here 25 and I will just set the value. So you can see over here, the temperature will now rise to 25 degrees Celsius. So this is a very crucial step because most of the sample, as I have mentioned, they are already, they are highly dependent on the temperature, and it is always good to always control a temperature very, means like very well. So you can see this is the geometry. This is parallel plate 50. We do have different sort of geometries with our system. So if you want to look at the concentric cylinder, so this is how the concentric cylinder geometry looks like. We also have a cone plate. This is a cone plate geometry. This is called CP50. 50 is the diameter of this geometry. And you can see this cone is basically inclined at 1 degree angle. So it is really very hard to see the cone, but this type of geometries do have a cone and a truncated center. So the center of these geometries are somewhat like truncated up to 50 micrometers. These are also very extensively used, but as I have mentioned, the limitation of these geometries are the particle sizes, that you cannot use these geometries for particle sizes which are like bigger than 10% of gap. And basic advantage of these parallel plate geometries are that you can actually change the measuring gap, which will enable you to measure the sample which are having a bigger size particles. So I'll be using this parallel plate geometry. I'll put it into the coupling unit, and that's it. So here you can see each and every geometry that we have comes with the tool master. So once you plug your geometry in the rheometer, it will automatically detect. So you can see over here, the measuring system it is right now detecting is PP50 that we are using, and the cell, that is the temperature device, we are using PPTD and HPTD both. And right now our temperature is set to 25 degrees Celsius. Now we will move to the measuring position. The measuring position. So the flexibility with the a parallel plate geometry is that you can actually move the measuring gap. Although in case of cone plate, you have a fixed measuring gap. So you will see now Yeah, you will see now the head is moving down towards the sample. So after it reaches the measuring distance, it will ask for trimming, which is also very much crucial because you only want to consider the sample which is in between the geometry and not not the sample which is outside of geometry. So you can see over here, you can see the extra sample is spilled out. So we need to remove this extra sample in order to effectively measure the flow curve. So I'll just trim the sample. Trimming is very crucial for any rheological measurement because in case if trimming is not done properly, then the results may vary. So after trimming, I'll just close this hood to make it means to make it thermally homogeneous, and then I will continue with the measurement. So I'll go to the flow curve because I am right now interested in the flow curve of this particular sample. So I'll just click on the flow curve and you would see that a complete flow chart of how this experiment is going to be will go forward, or how this measurement will take place. You will find out all the information in this flow chart. Here you can see the devices what we are using, the temperature. Then it will automatically switch to the diagram, where in diagram you would find the viscosity and the shear rate, or you will also find the shear stress versus shear rate. The most important part is the measurement, where you can actually decide your parameters. So in this case, what we have over here is the parameter from 0.1 second inverse to 100 second inverse of shear rate. In case if you are not willing, or you are more comfortable with RPMs, then you can also change this shear rate to RPM. We have a lot of parameters over here which you can actually play with, and also then you can decide about the time period for each measurement. So usually whenever we consider any particular flow curve, you can see over here shear rate is always have a unit of second inverse, that is inversely proportional to time. So the whole idea is to keep the time, measurement time, more than what the reciprocal of shear rate. So for example, if your minimum shear rate, or you want to start measurement from 0.1, so the initial time should always be more than the reciprocal of 0.1. So for if you divide 0.1 1 by 0.1, it would be 10. So initial time for rheological measurement should always be more than, or you can say 3 times that of your first shear rate, or first minimum shear rate. So here you can see for 0.1, I have selected 30 seconds of time, and for 100 second inverse, 1 second is also enough, but usually I keep it 10 seconds. And in calculator, we can decide that we can put 4 points per decade. Now, most of the times when we talk about rheological measurements, we are dealing with logarithmic curves, or you can say logarithmic scale. So it is really very important to decide how many points do you want per decade. Usually, for most of the application, 4 points per decade is more than enough. So that means in a scale of 10 to 100, you would have 4 points that we will see. Then there are different analysis templates like regression, interpolation, or as Dr. had mentioned, that which is as Dr. had mentioned that we have means like we can determine the yield point using a rheometry. So there can be different analysis regressions to determine yield point depending upon the type of shear thinning liquid that we have. Usually there are few models such as Herschel-Bulkley, which we would be using over here. And then there would be a Kaysen model and also Bingham model. So depending upon the behavior and the properties of your fluid or liquid, you can actually select either of them. So this is also a way to determine the yield point of the sample, and also in case if you want to determine the zero shear viscosity, you can do that. I'll show you after the measurement. So let me start the test. So I'll just click on the start button and I'll just put test and continue. Most of the times it is always very important to put some waiting time before the rheological measurement in order to gain thermal homogeneity, because you need to be really very sure that the sample what you are measuring is thermally homogeneous, means there is no gradient present. So usually for right practice is to keep like 3 minutes of time before measurement. That also depends upon the sample. Of course, if you are measuring some sort of volatile sample, then it would be like difficult to give that much of time, but still you should make some way to make sure that the temperature inside is very much homogeneous. So we do have a special type of geometries for volatile liquids also with the solvent trap. So this will start in 1 minute. So surveillance time is given 1 minute. Now it automatically switched to the graph, and you would measure the first point in 30 seconds, and then the time period would vary logarithmically. The data file, what you would have will appear over here in this tab, that is the table tab. And also after the measurement, you can get a report. So you can see this is your first point, first viscosity point. So the viscosity at 0.1 second inverse is approximately 1000 millipascal seconds. You can also change the scale in case if you want. And on the right hand side, you are looking at the stress versus shear rate plot. So you can see that first 3 points are pretty close to each other. Means the value does not changes much. So 4 points per decade would mean that there are 4 points in 1 decade. So this is an ideal, I would say, ideal parameter that most of the users uses. That is 4 points per decade. And now you can see at a around say at 0.5 second inverse. After that, the viscosity is still it is somewhat stable. So you can see there is a shear thinning nature, but at a lower shear rate, definitely when you talk about the surfactant, they do have a longer molecular chains. And when you talk about a longer molecular chains, usually they are entangled. And at a lower shear rate, as I have also mentioned earlier, at a lower shear rate, uh, there is a continuous entanglement, re-entanglement and disentanglement. So you will have a constant value of viscosity. That is, your viscosity value won't change much. But as you increase the shear rate, your disentanglement will actually start to overcome your re-entanglement, and your viscosity starts falling. Also, you can see the Herschel-Falkley fit over here. So you can also measure the yield point using this particular model. In case if you want to determine the zero shear viscosity, so you can select this particular data, and then you can select the analysis for zero shear viscosity, which is mainly Carius-Yasuda. So you can see various mathematical models in this. Just make an analysis tab and then probably it out. So I can just go to analysis, and I can just add an analysis tab where I can, in case if you have some analysis of your own, then probably you can select it. Yeah. So you can see over here molecular mass. You can also, if you divide it into, so here you can see it will actually give you an Carius-Yasuda, the zero shear viscosity as per Carius-Yasuda, and it will also give you the molecular mass of your sample. So only thing is that you need to input your data file. So I'll input it. and then I can just run a start. And see whether it's because usually we have this Curious Suda in the test template. It is not working in that because it's asking for that some other parameters. Anyways, there is, I need to make a analysis template for that. So I will be making it and I will show you tomorrow with an oscillatory test, how to do a zero shear viscosity, because I think it has been removed from the analysis tab, and I have to make it by myself, or I have to save the macro accordingly, and I'll be doing it, and I'll show you tomorrow how to determine the molecular mass. Zero shear viscosity of these type of cells. So ideally what it would do is it would fit a zero shear viscosity curve as what I have shown you in the presentation, where it will actually extend this plateau, it will extrapolate it, and it will give you a value of a zero shear viscosity. So this is something which is very important in order to determine the molecular mass by Mark-Hoving's equation. Now, Mark-Hoving's equation actually is related to, that is a mathematical formulation, of course, which also requires some material constants. And we also have an inbuilt material constant library with this particular software. So you can see over here, when you go over here to parameters, so you can see over here the material constants. So depending upon what material you are testing, you can select this K and A value. Because in case if you are measuring or you are means like determining the molecular mass through mathematical calculation, then you need to use these material parameter constants. And also then other than that, we can also perform other analysis like Cox-Merz. Cox-Merz is basically for viscoelastic effect that we will be discussing tomorrow. Yeah, then you can fit your curve by power law. You can determine the power law slope, and also you can do yield point by Bingham. So if in case if I select it, then sorry, I need to select this one. I can select this stress and strain, and I can just go ahead with the Bingham and see what are the analysis results. So you can see as per Bingham, the yield stress of this particular material is 2.44. And as according to your applications, of course, you can apply different sort of models, mathematical models, which are present in this. So, and again, then there are various other tests like thixotropy, which you can also use. So I'll quickly show you the parameters, what is being used for thixotropy. So you can see over here, if you go to the measurement of 3-interval thixotropy test, you would have 3 intervals. First interval is at a very low shear. Second interval is at a very high shear. And third again is at a very low shear. Here we would be measuring the sample with 3 different interval and will be determining the I would say means like some structure recovery behavior. Let us check some examples of sample, and then we can just. So for example, if you have a paste-like sample, you can see over here the viscosity curves for 2 different type of paste-like samples, and also you will have these are you would also have a yield stress as per Bingham. So this is a emulsion. This is not paste. This is basically an emulsion sample, and you can also determine different yield stresses with the flow curve. So you can see the difference between 2 emulsion samples over here. What I want to show you is something related to polymers. So I'll let me go back. So we have a different examples of different sample and different type of measurement. Check this one. Yesterday. Yeah, so this one do have a, I'll save it as a macro. So we have a regression like Yesuda. I will go back to our analysis. Check over here, then select it. Let us see now if it works. Insert. Yeah, so we have it over here. So then I can, so if you go into details of Yesuda, You can also find out what are the equations that it is using. So I'll click over here. So this is a basic mathematical equation for Carius-Yesuda in order to get the zero shear viscosity. So I'll select a file. I'll select the input parameters. I'll select the test file. The viscosity one. And I will start and let us see. Okay, so usually it is not working because in Carius-Yesuda it is the mentioned parameter is complex viscosity, and here we are doing a viscosity, normal viscosity. So let me change the variable over here. Here I will go from shear oscillatory to, sorry, I will go to shear standard study. And then I can select the variable. So my variable is, X variable is shear rate, and my Y variable is viscosity. And that is it. So I have changed the variable. Now let us see. Now it works. So if you go to the diagram and you select this, and you can get the curve as per Carius-Yesuda. So you can see it had extrapolated the viscosity curve, and at a low shear rate you can see that it is giving you a zero shear viscosity of 1047 millipascal second. And as you increase the shear rate, there is a shear thinning behavior with this particular type of sample. Now this value 1047.3 can be used for determining the molecular mass that we can use with the, for example, with from Howing's equation. So I'll just add another analysis tab. Let us see now. So I'll just insert this. Check the material parameter, the text. So in case if I am using LDP or HDP, I can change these material parameters depending upon this library. I'll input the values. So let me input the Foxmer's or the viscosity value of Carius-Yesuda. Let us check if it works. So now you can see over here the molecular mass. So you can see according to that material parameter, the molecular mass, what it is showing is 1.0 grams per mole. So this is not correct, of course, because we have used a wrong material constants. But in case if you know the material constants, then you can very easily calculate the molecular mass of animal. So this is something which is very important, especially in case if you are doing any sort of molecular mass studies for polymer solutions and polymer melts. So this is a very useful tool or analysis mode which you can use to characterize yourself. Other than that, there are various other tests, and you can design tests as per your own requirement. So if you want to simulate any actual conditions, you can do that. So this is it for today. I think we have extended it a bit long, but sorry because of the troubles what we had earlier, and we would definitely try to compensate that tomorrow. And in case if you have any questions, I am open for that, and you can get it.
Thank you, Dr. Ornov, for the nice Lego demonstration, and thank you, Dr. Muhammad for the very nice presentation. Actually, there are some questions in the chat box. Let me tell you the first question from Ms. Rasha Al-Ghazawi, Egyptian Petroleum Research Institute. She's asking, would you please clarify at what shear rate did you measure the viscosity via temperature for ABU crude oil and treated ones with different concentrations of ROA?
Hello. Should I answer?
Yes.
Yes, you should. It is for you.
Actually, I've written down for her the chat an answer to this, that we use different shear rates and ranging from 1 reciprocal second up to 50. So for every viscosity temperature run, we've done it for a constant viscosity, for a constant shear rate. So we use the shear rate just to mimic the about to stop flow, about to stop, and then we use the 50 reciprocal second to mimic the flow production in the pipeline. So as long as you use one just constant shear rate, and you just monitor the change of viscosity with temperature at that shear rate. Is that clear enough?
All right. Thank you very much for the answer, Dr. Muhammad. Dr. Misha, if you have any comment on the answer, if it's clear or not, please let us know. And there is another question from her side also. Would it be useful to measure the viscosity by temperature curves for the crude oil? I think it's the same. And the treated ones at less than 40 Celsius to match the pour point of the crude?
Yes, why not? Since if you can measure it, you can compare it with others or the other temperatures, and the increase of viscosity, this will give us also hints about the strength of the gel format, you know. So if the range can be measured, that's why not?
That's great. And I'd like to add something regarding measuring the viscosity and pour point. Dr. Ornov, let's talk a little bit about our SVM 3001 called properties, which is able to measure viscosity and go down to very low temperatures and can measure the cloud point and the freezing point as well as cold flow properties along with the viscosity with the same instrument.
Yes, we can measure the cold flow properties using SVM. Only thing is that for SVM, the technique itself is completely different, as you all probably know. So there we are measuring the dynamic viscosity and the density of the material, and then we are dividing the dynamic viscosity with the density to get a kinematic viscosity. So ideally, SVM is very much suitable at normal temperatures for Newtonian fluids, although means like as you know, means like if in case if there is a wax present in your sample, of course there will be some sort of crystallization, and then it will transform from Newtonian to non-Newtonian fluid. But still you can determine some cold flow properties using SVM. But yeah, means like, but for usually, in general, SVM is more useful for Newtonian fluids compared to non-Newtonian fluids. Yeah.
All right, thank you. And another question from Dr. Rasha. Would you please help me in selecting the low shear value that I can choose for a paste sample to simulate a process of start pumping the paste through a nozzle?
Yeah, so this is something which definitely, so paste sample, you can choose any of the lower shear rates in order to measure any paste sample in a rotational mode. But the problem with the paste samples is especially when you are working at a higher shear rates. So you need to be sure that there is no wall slippage, because paste samples usually at a very higher shear rates, there can be some wall slippage which can happen to your sample. So your torque value suddenly reduces. So ideally, I would say that in paste samples, in case if you are going to measure it in a rotational mode, then lower shear rate, you can choose any of it. Maybe you can go ahead with 0.001 second inverse. But high shear rate is something which is you need to be careful of. Second point is, if you are choosing a very low shear rate, you need to make sure that you are giving an ample amount of time for a measurement. So for example, if you are going to measure a sample at say 0.001 second inverse, then the time period for the measurement or measurement of that particular point, it should be more than reciprocal of that. So the reciprocal of 0.001 second inverse would be 1000 seconds. So you need to give at least 4000 seconds or 5000 seconds in order to measure one single point. So that those type of experiments would take like forever, you can say. So ideally, most of the times, even in case if you are starting from say 0.01 second inverse, this is good enough. It's like you would get almost every information of your particular sample. So I would say that you start with the 0.01 because it will also not take much of the time for the measurement, and you need to take care of high pressure, high shear rates, because in paste samples there can be lot of walls. One alternative we have, we will talk about it tomorrow, is that if you ask any rheologist who are actively working in this particular field, they would always suggest to measure paste samples in oscillatory mode. Why oscillatory mode? Because you don't have a probability of any wall slippage, or there won't be any loss of the sample while working at a higher rate. So I would say we'll discuss it tomorrow, the oscillations. And if you ask me, you can work, you can use paste samples for rotational method in a rotational mode, but oscillations are always preferred. And then you can compare the complex viscosity with the viscosity of your shear, rotational shear, steady shear methods. Yes.
That's a great idea, Dr. Onov. And thank you very much for the detailed answer. And I hope this was enough for you, Dr. Rasha. Thank you. And the last question in the chat box was from Miss Marwa Isa from Sarir Oil Operations. She is asking if the link invitation of tomorrow's session will be the same, or
no, this is the same. You can just log in into same link, and then we will start it with this same link only. So it would be same link. There is no extra link, and after that session, you would get the question paper, your question paper in say day or two time.
All right. Thank you very much, and thank you all for attending the session. Thank you, Dr. Onov. Thank you, Dr. Muhammad. Thank you, Dr. Fathiya. We had the honor to cooperate with Libyan Petroleum Institute in such an event. And please, all attendees, wait for our second and final session tomorrow. And there will be an exam in order to be solved and get the final certification of attendance of the event. Thank you very much, and see you tomorrow.
Okay.
Thank you very much.
Thank you.
Thank you very much.
Thank you very much for your time.
Thank you for all. Thank you for all. Thank you.
Thank you. Goodbye.
Bye.